Alright, Calvin Ho, Engineering 2030, Homework 2, Problem 1, the tugboat problem. So we're given the total weight right here, that 3,600 kilonewtons. We transfer that to kilograms using the knowledge that mass equals weight over gravity. We get that. And we're also given that this force equation, yeah? Okay. And we're asked to find A, the time for V naught, 1 meter per second, going to V equals 2.5 meters per second. Then we're asked to find B, the distance traveled in that time. So for our boat, we make our free body diagrams and kinematic diagram. In free body, we have this F force of the boat moving forward and tugging that boat. I'm tugging the load. We have gravity pulling the boat down, and we have the normal force of the water, buoyancy force. And then we know that it just accelerates over here to the left, and we have this being our x direction and up being our positive y direction. Okay? So we use our F equals ma. Transfer that, we know F net equals the mass, yeah, that we found, times acceleration in the x direction, yeah, and that's F net because that's all that travels through it. Plug in our values and we get AX equals this right here. Okay, so part A. So we know that V naught and the V final that we're trying to find the time for, we know that AX equals dV dt. So we transfer that around and we do dt equals dV over AX, sorry. Okay, we integrate that, dt 0 to t, and then the other from 1 to 2.5. Then we find that t equals that equation right there. Plug in our values and we have the time it takes from V naught to go to V equals 18.84 seconds. Yeah. Okay, part B, we're looking for how far it travels. So we know V dV equals AX dx. Transfer around, we know dx equals V dV over AX. Integrate both sides. And then we get x equals m over this 27,000, that right there. Plug in our values, 1 to 2.5, and then we get this x equals 36.14 meters. Yeah. Okay, and that is question 1. Okay, question 2, and this, let me flip my notes. This is the truck, okay? So we're given the weight of the truck, the weight of the boulder, and the weight of the pallet. Knowing that mass equals weight over gravity, we're able to convert these weights to find the masses. So an example for the truck is at 155.28 slugs right there for the boulder, and then 6.211 for the pallet. Okay, A. Oh, and sorry, we're also given the acceleration of the truck equals 1 meters per second squared to the left. Okay, so part A, we're asked to find the horizontal force between the tires and the ground. And then B, we're asked to find the force between the boulder and the pallet. So we're going to set up some free body diagrams. This is for the boulder and the pallet being held by these pulleys. So here's the pulleys, tension equal on both sides, gravity pulling the mass of the pallet and boulder down. and then right here the acceleration of the pallet and boulder up. Okay, so we know xt, the x of the truck, so the length of the truck rope, minus 2yb, so 2 plus the rope, 2 times the rope length to the boulder is a constant. Derive that and we get velocity t minus 2vb equals 0. Derive that again and we get at minus 2ab equals 0. Change some stuff around and we get the acceleration of the boulder equals 0.5 meters seconds squared. Okay, and then for our free body diagram up here, we sum the forces in the y direction. We get this right here. So this side equals this side. And then we solve this for t, and we get this 609.32 pounds for the tension. Okay, so the tension that it feels here. Okay, we set our next free body diagram. This one is the one for the truck itself. We have the force forward on the wheels and the ground, normal force up, gravity down, tension of the rope, and then we know it has to equal the mass of the truck times the acceleration of the truck, so that force there, because it is accelerating forward. So we sum those forces in the x direction for the truck. Get that right there, F minus T equals MTAT, and we get the force of the tires and the ground equals the 765 pounds. Okay, on to part B. In part B, we're looking for the force felt between the boulder and the pallet. So we set up this next free body diagram. So this is the boulder itself. We have the mass of B times the gravity going down, the force of the pallet plus the boulder going up, and then has to equal the acceleration of the boulder itself going up. So that is that mb times the acceleration of b. Okay, we're going to sum those forces in the y direction. So we get right there. And then we know that the force, figured out for this force here that the pallet applies on the boulder, and we get this 101613 pounds on that. Add the units on that. Pounds. Okay. So on to question 3. Oh, and this, from my notes, this should be a positive sign. So that right there. Okay. Oh, actually, no. That was right. That was right. My apologies. So that is right. Okay. All right. So on to this next one. This one is going to be the tetherball one. Yeah, this one's going to be the tetherball one. So we are given the grams of the tetherball, which is at 450 grams. We are given the velocity of the tetherball, which is 4 meters per second, and we want to find the angle theta, and then we want to find the tension in the cord. Alright, So we know the acceleration of the normal right here equals v a squared over this. And then we also know that the sine theta equals that right there, and we solve it, and we know this value here equals sine theta times the length of AB. Okay, we set up our free body diagrams. We have the weight of the ball going down, the tension it feels from the rope, and that theta there. And we know it has to equal the acceleration of the ball going in towards the pole, which is that ma times acceleration of a. Okay, so a, we're finding the angle theta. So we're gonna sum the forces in the y direction, and we know they have to be equal to 0 because the ball isn't accelerating upward, it's just accelerating in a circle. So this equals TAB cosine theta minus W equals 0 from that right there. And we get this value for TAB, the tension. Okay, and then we sum the forces in the X. We get this right here. And we know this needs to equal this, and we solve. Play around with some values that we had for TAB that we had up there. We had for the acceleration, and then we find that the theta equals 49.9 degrees. Okay. Then on to G. So we just find that angle there. Then, sorry, I must have lost my other page. Then we can find TAB just by plugging that in. So we know TAB equals this weight of A over cosine theta. So TAB equals this 0.450 kilograms times that gravity, meters per second squared, all over cosine of that theta we just found, 49.9, and that's going to equal 6.85 newtons. Yes, and this is going to be B. Okay, sorry about that. So that right there is going to be our B. Okay, moving on. So problem 4. Just turn my page. Okay, problem 4 is the one with the wrecking ball. So we are given the weight of the wrecking ball equals 130 pounds. Use that mass equals weight over gravity, and we find the mass of the ball is 4.03 slugs, and the length from A to B equals 45 feet. Okay, we're given that. And we're asked to find the tension at A, the top of the swing at C, and then as well as the tension at the bottom of the swing when the velocity VB equals 13.2 feet per second. Alright. So we're going to start with our free body diagram, kinetic diagram for the wrecking ball at C, where it's at the top of the swing, and we know when it's at the top of the swing, then the velocity of the ball has to be the 0, because it's at the very top and no longer goes forward. So we get that right there. So tension BA over that angle, the weight of B times by, and then this is the force of that normal as well as the force of the tangent, and then we do our acceleration, and we know the acceleration of the ball has to be equal to 0 since the velocity is 0. Yeah. Okay. Now we find this force, and let me grab my pen. Then we sum the forces in this kind of diagonal direction, and we know it has to be equal to 0 since the ball is no longer accelerating, and so because the ball isn't accelerating up. So plug that in right there, and then we know TBA has to be equal to this 122.2 pounds. Okay. Okay, part B, when it's at the bottom, we have a new free body diagram. This is our tension, BA, we get rid of that angle. We have this weight of B down, and then we have our forces for the normal and the tangent. Okay, some of the forces in the Y. We get this TBA minus WB MBAN. Solve that for TBA, we get 145.6 pounds. Okay, and that is it for 4. Okay, number 5. Five is the turntable. Cool. Okay. So we know that B slips after 10 seconds. Okay. And we know the acceleration, the constant tangential acceleration is at 2.4 meters per second. So that's right there, ABT. And we're asked to find the coefficient of static friction between the trunk and the turntable. Okay. Okay. ABT implies uniform acceleration. Yeah, equaling a constant implies uniform acceleration. So we use our equation that V equals V naught AT. And then at 10 seconds, we know that the initial acceleration is 0 because it starts from rest. 0.2 times 10 seconds, and that B has to equal 2.4 meters per second right there. Okay, and then we're going to draw our free body diagram for the trunk. We know right here it has since it's spinning, it has a force inward. And then we have our M times acceleration, B tangular, and then the normal. Okay. Okay, so we're gonna sum of the forces. Okay, we know the sum of the forces is equal to that, and we know that the magnitude of the force has to be equal to this right here. All right. And then we're going to sum, let me see, sorry, just looking through my notes. Okay, sum of forces in the Y, since it's not moving upward, has to be equal to 0. So we get that N times W equals 0, and this is for that free body diagram right here for that trunk. So it's N, normal force up from the turntable, W of the trunk itself, and this is that force it feels from the centrifugal motion going inward. Okay, equals, so we know N has to equal that mass of the trunk times gravity. Okay, and at 10 seconds, that force equals the friction force times the normal. That's what, the coefficient of static friction times the normal, because that's that friction force. And then we know the normal has to be equal to the mass of the trunk times the gravity. Right here, right? That's what we just found. And then we know that this right here has to be equal to that force it felt. So the force between them is this right here that we found earlier. And then we solve everything for this static coefficient. Then we get it equal to 0.236. That's going to be it for 5. Okay, this one is the orbit of the planet Venus. Alright. So we're given the orbit velocity, was that right there. We are also given the distance between Venus and the center of the sun, which is that right there. We're given the radius of the sun, and we're asked to find the mass of the sun, the acceleration of gravity at the surface of the sun. Okay. So, we set up our force equation that we have. We have big G, big M, which is going to be the mass of the sun, times little m, which is Venus, times the radius of them squared. Okay. And we get that right here. Okay. Solve for values. This is our other force equation. We know they have to be equal to each other, and then we solve it. And then we get big G equals big M equals the radius times their velocity squared. Okay, and then we solve for A. We use this equation we just found. We solve it for the big M, which is the mass of the sun. Plug in our values, and we get 1.998 times 10 to the 30 kilograms. Okay. B. Define the acceleration of the gravity of something at the surface of the sun. So we know this G, big M, little m, r squared, and we know it has to equal to the gravity something feels at the surface of it, which is equal to small m gravity of the sun. So just the mass of something, gravity of the sun. We know the little m's cancel, and we just have G for gravity of the sun equals big G, mass of the sun, r squared. And we get, radius squared. And we get 276 meters per second squared. Okay, and that is problem 6. Problem 7. Okay, this is the one for the particle of mass. And we need to show that F is inversely proportional to the square of R. Okay? So we take what we know. We know R equals R naught 2 minus cosine theta. Take this other equation that we know. And then we're going to solve it for F. We're going to solve it for F. This equals the 2mh squared r naught times 1 over r squared. And then we know these are all constant values. So r naught's a constant, 2, mass is a constant, this h is a constant, 1 over r squared. So because we know those are constants, then we find that the relationship between f and radius equals f equals 1 over radius squared. Yeah. Yes. So moving on to problem 8. Sorry, just reading some of my notes on this next one. This one was kind of tough. So this one is going to be the satellite, and we're given that the altitude is this 19,110 kilometers above the surface of the Earth. And we're asked to determine A, the increases speed of A for escape velocity, as well as B, the decrease in speed. The decrease in speed required to reach the minimum point of this 6370. Alright. So we know the velocity of the circle has to equal that equation right there. Solve it, and this is our velocity that we get. This is 3452.5 meters per second. We know that the escape velocity is looking like that right there. So we get this 5589.7. Yes. 0.7, and we know that the velocity change is equals to the escape velocity minus the circular velocity, which equals that right there, and that's how much that is going to need to increase in order to escape. Okay, so that's A. And B, the speed decrease we need to reach that minimum point. Okay. So we know R at that minimum point. So the RB equals 2 times that. And we're going to get that 12.740 kilometers. Setting up our equations that we know. This is for our A point. Then this is going to be for our B point. We know that the theta of B equals theta of A plus 180. So we can conclude that cosine theta A equals negative cosine theta B. That allows us to set up this 1 over RA plus 1 over RB equals that right there. And we're able to put that this equals to that 2gmh squared. And then solving for h, we get the 82.230 times 10 to the power of 9 meters per second squared. And then we know that the change of velocity has to be the circular velocity minus that VA for that smallest point. we didn't discuss VA. So VA equals this H over RA. And we find this 3.22 right here times 10 to the power of 3 meters per second. Then, like I was saying earlier, this change in V, we know it needs to decrease 725 meters per second in order to reach that minimum point. Okay. And then C, we need to find the eccentricity of the ecliptic orbit. So we know this RA minus RB, RB equals the C cosine theta B minus cosine A, and we can conclude that equals 2C. Solve for C, and this equals 19.6 times 10 to the power of negative 9. Okay, so A, 9, last one. We're just asked to basically show that we can derive this function that we derived down here, but we'll start from the beginning. So we start with what we know for this initial point, for this R initial, and then we have this RB that we have, so that's going to be the other side. We know theta B equals theta A plus 180, and then we can conclude that cosine theta A equals negative cosine theta B. That allows us to add together and set up this equation here, much like we did in the last problem. Then we know that our acceleration normal equals this V squared for that P. Change over that values for V, and we got H2 R squared. That right there. Then we set up our force equation. Now F of the normal is that G, big M, small m, R squared, and that has to equal that mass times acceleration of the normal. We get Fn equals that. Changing around some values on it. And then we solve for this right here. We know that equals Gm, and right then squared, and then it equals 1/2 1 over R theta plus 1 over R1. Gmm. Yeah, equals that right there. And then we're all good. Okay, thanks.